Okay, let's go to May, June 2024. Paper 41. Found the paper? Yep, found the paper.
For Adrian.
These are your syllabus. Okay. Define gravitational potential at a point.
Force directly proportional to no, sorry. Work done per unit mass in moving a mass from infinity to the point.
Okay. Work done per unit mass in moving the mass from infinity to the point. Right? And equation from the formula sheet. The satellite X have a mass m, orbits a planet at a constant distance for r from the center of the planet as shown in figure 1.1. Second, planet Y of mass 2m orbits a planet with a radius r. Gravitational potential at x due to the planet is -5. The planet is uniform sphere. Explain why gravitational potential at x is negative. Yep. Can first, potential is 0 at infinity. That's your first point. Work is done by the two masses in moving closer together. Basically, the force is attractive. So the work is not done by you. Work done is by the two masses in moving closer together. Right? Okay. Either moving closer together or work is done on two masses in moving apart. State in terms of y the gravitational potential at y due to the planet. Right? Let the planet be m, the mass of planet be m. There's your y, right? Planet y. So write down there. That one is given in the formula sheet. Right? Rewrite that. -5 for r. And then capital the m. We do not require this m. We are requiring this m. Right? I got it wrong till I figure out today. Then take the 4 across arrow. Get gm over r is -f. And for y is gm over r. So gm is -4. Okay or not?
Yeah.
Don't make the same mistake as me. We don't use this mass. No, use this mass. We use this mass of the planet to find the potential. Gravitational field strength of planet X and satellite Y, and gravitational potential energy of satellite X and satellite Y. Okay. Okay, that's what we get from previously. Right, certified Y is -4. And electric field strength is sorry, gravitational field strength is Gm over R squared. Or Gx, Gm over 4R. 4R squared is 16R squared. 16R squared, right? Gm over R. Gm over R is 5 lah. Use this one. Cancel the minus sign there. Gm over 4R. And Gm over 4R. There's still an R and a 4 there. And Gm over Y. Gm over R squared. Okay, Gm over R is 4 over R. Fill it out. Okay. Initially, I got it wrong. But to be honest with you, I also try to figure out this marking scheme wrong until this yesterday or today, this morning. I just sorted it out. State the magnitude and unit of absolute zero on the thermodynamic temperature scale. Yep. Yep. What's the value?
Give me a moment.
0 Kelvin, no? Explain why temperature measure using laboratory liquid in gas thermometer does not give a measurement of thermodynamic temperature. Yep.
The measurement using liquid in the gas thermometer depends on the properties of the liquid.
Measure depends on properties of the liquid. Basically, very hard to interpret syllabus. We would have thought this one will be briefly. Right? Precision thermometer, they have removed the advantages and disadvantages completely. But then it came out. Anyway, it's in your note. I've given you your note. So you have to start stretching a bit. When you study for revision, start stretching a little bit. Figure 2.1 shows a simplified diagram of a type of thermometer called a platinum resistant thermometer. The glass tube is immersed in an environment from which the temperature is to be measured, which is to be determined. The resistance between the terminal X and Y is measured. Figure 2.2 shows the variation in resistivity of the platinum thermometer, resistivity of the platinum with the thermodynamic temperature T. Explain how figure 2.2 shows that the platinum is suitable metal for use in resistant thermometer. Yep.
Resistivity varies linearly with temperature.
You want it linear, varies with temperature. Right? One value only, not like some got two value. One value of resistivity, one temperature, that's a requirement. Second point, variation with temperature is linear. It's a straight line, not a curve. Right? Liquid in glass is a curve. These are the answer lah. Alternative answer. Suggest a reason why platinum resistant thermometer is not suitable for measuring rapidly changing temperature. Yep. They didn't say about the advantage and disadvantage lah.
Because like I remember this one is like takes time to respond, basically.
Take time to respond. No? Thermometer takes time to reach the correct temperature. Take time to respond. No? Suggest a type of thermometer that is suitable for measuring rapidly changing temperature.
Digital thermometer.
Thermocouple.
Oh.
Right? Thermocouple is basically two metal joined together. They can respond very fast to change in temperature. Whereas resistant thermometer takes a while to respond. Right? These are alternative answer lah. A negative temperature coefficient thermistor may be used as a type of resistant thermometer. State one way in which the variation with temperature of the resistance of a thermistor differs from that of a platinum wire.
The thermistor resistance decreases with increasing temperature. Variation is inversely proportional
Denominates,
and non-linear.
right? Either non-linear or is it variation is inverse. As you say, as the temperature increases, the resistance decreases. That's the alternative answer. Say what is meant by ideal gas.
Do you guess?
Yep.
Obeys the PV over T, the constant. P equals pressure, gas, V is the volume, T is the thermodynamic temperature.
Gas for which PV is proportional to T, where T is a thermodynamic temperature. Use one of the basic assumptions of kinetic theory to explain what can be deduced about the potential energy associated with random motion of molecules in an ideal gas.
What's this? Like the intermolecular forces are negligible. Potential energy is zero.
Okay, no intermolecular forces. The potential energy is zero, okay? This one is calculation. Volume is given, pressure is given, temperature is given. Just choose the right formula. PV equals to NKT. So N is PV over KT. So put in your value. That's your pressure. That's your volume. This one get from your data sheet. Right? This one is given. Calculate out. Average translational kinetic energy of one molecule of a gas. Yep. How do you calculate? What formula to use?
V equals nRT equals NKT.
Right? Just use kinetic energy formula. 3 over 2 kT.
Yeah.
Right? This is your K value. This is your T. value. Okay. You cannot remember,
Okay.
derive it. Internal energy of the gas. Explain your reasoning. How to calculate internal energy of the gas?
Well, let's keep total kinetic energy plus potential energy of all molecules. Actually, potential energy is zero for ideal gas. So it's internal energy is total Ke.
Okay, we have calculated and E we have calculated. Right? Potential energy is zero, internal energy equals total kinetic energy of molecules. So it's N times E. E is for one molecule, so times N. Okay. Any comment?
Yeah, no.
Volume of the gas is now varied, keeping pressure constant. Sketch a variation with V of the internal energy of fuel of the gas. How are you going to sketch the graph? Go to the equation. No?
Just going up, right? Like that's from zero to up.
Right? Go to the equation.
Straight line.
You want U in terms of V. Right? So kinetic energy is 3/2 kT. U is times N, that's all. Then NKT is PV. No? Right? Pressure is kept constant. So it's a straight line. No? Passing through origin. No? Okay. Usually they'll ask you to derive, use the equation, calculate. So you go back to your question and then derive the equation. No? Okay. We have used this formula. This is a given formula, equation of state. Yep. Can
Yeah.
what is meant by resonance?
Um, maximum amplitude oscillation, maximum amplitude, or let the frequency equals to natural frequency.
Hmm. Oscillation object is at maximum amplitude when the driving frequency equals the natural frequency of the system. A small ball
Okay.
is held in place using a stretch string. One end of the string is fixed to the wall, and the other end is attached to a vibrating vibrator as shown in figure 4.1. Right, there's a vibrator. Initially, the vibrating generator, the generator is switched off, right? That one cause vibration, go up and down. So initially it switches off. The student displays the ball vertically and then release it. Figure 4.2 shows the variation of the displacement of the ball with time after its release. State the name of the phenomenon illustrated by the decrease in amplitude of the oscillation. Yep. What do you call this type of oscillation?
Damping.
Not diffusion, light damping, heavy damping, critical damping.
Oh, eh, I think it's light. Then
Light damping, no?
how is it like the big?
Light damping,
Is it
you will
because
have
like
oscillation, the amplitude decreases slowly. Critical only show this part. Heavy damping,
or if it's heavier?
heavy damping, it doesn't touch the line. It will it will take a long time to touch the line. Okay?
Oh, I see.
Explain the
Okay.
decrease with time of the amplitude of the oscillation of the ball. Yep. Can?
Oscillation of the ball lose energy due to like the resistive forces
Oscillation of ball loses energy. Why? Due to resistive forces acting on the ball. Okay,
the air resistance.
just say resistive force. Protect yourself. Determine the frequency of oscillation of the ball. Right? Just take the maximum and the maximum. Time between maximum to maximum, or minimum to minimum. Maximum to maximum, or minimum to minimum. Period is 0.25. Okay. Anytime we cut off already lah. So I see you next week lah.
All right.
Direction of generator in B is switched on and the frequency of vibration is gradually increased from 0 to 10 Hz. Sketch the variation with time f of the amplitude of oscillation of the ball. Right?
Highest amplitude is at 4.
Just that way, no?